In electromagnetism, the electromagnetic tensor or electromagnetic field tensor is a mathematical object that describes the electromagnetic field of a physical system. The field tensor was first used after the four-dimensional tensor formulation of special relativity was introduced by Hermann Minkowski. The tensor allows some physical laws to be written in a very concise form. Definition: the electromagnetic tensor, conventionally labeled F, is defined as the exterior derivative of the electromagnetic four-potential A differential 1 form. Therefore F is a differential 2 form, that is, an antisymmetric rank 2 tensor field, on Minkowski space. In component form, SI units for Maxwell's equations and the particle physicist's sign convention for the signature of Minkowski space will be used throughout this article. Relationship with the classical fields: the electromagnetic tensor is completely isomorphic to the electric and magnetic fields, though the electric and magnetic fields change with the choice of the reference frame, while the electromagnetic tensor does not. In general, the relationship is quite complicated, but in Cartesian coordinates, using the coordinate system's own reference frame, the relationship is very simple, where c is the speed of light, and where is the Levi-Civita symbol. In contravariant matrix form, the covariant form is given by index lowering. The mixed variance form appears in the Lorentz force equation when using the contravariant for velocity, where from now on in this article, when the electric or magnetic fields are mentioned, a Cartesian coordinate system is being assumed, and the electric and magnetic fields are with respect to coordinate system's own reference frame, as in the equations above. Properties: the matrix form of the field tensor yields the following properties. Antisymmetry. 6 independent components. In Cartesian coordinates, these are simply the three spatial components of the electric field and magnetic field. Inner product. If one forms an inner product of the field strength tensor, a Lorentz invariant is formed, meaning this number does not change from one frame of reference to another. Pseudo-scalar invariant. The product of the tensor with its dual tensor gives the Lorentz invariant, whereas the rank 4 Levi-Civita symbol. The sign for the above depends on the convention used for the Levi-Civita symbol. The convention used here is determinant, which is proportional to the square of the above invariant. Significance: this tensor simplifies and reduces Maxwell's equations as 4 vector calculus equations into 2 tensor field equations. In electrostatics and electrodynamics, Gauss's law and Ampere's circuital law are respectively, and reduced to the inhomogeneous Maxwell equation, whereas the 4 current. In magnetostatics and magnetodynamics, Gauss's law for magnetism and Maxwell-Faraday equation are respectively, which reduced to Bianchi identity, or using the index notation with square brackets, note 1, for the antisymmetric part of the tensor. Relativity. The field tensor derives its name from the fact that the electromagnetic field is found to obey the tensor transformation law. This general property of physical laws being recognized after the advent of special relativity. This theory stipulated that all the laws of physics should take the same form in all coordinate systems. This led to the introduction of tensors. The tensor formalism also leads to a mathematically simpler presentation of physical laws. The inhomogeneous Maxwell equation leads to the continuity equation, implying conservation of charge. Maxwell's laws above can be generalized to curved spacetime by simply replacing partial derivatives with covariant derivatives, and where the semicolon notation represents a covariant derivative, as opposed to a partial derivative. These equations are sometimes referred to as the curved space Maxwell equations. Again, the second equation implies charge conservation. Lagrangian formulation of classical electromagnetism. Classical electromagnetism and Maxwell's equations can be derived from the action, whereas over space and time. This means the Lagrangian density is the two middle terms in the parentheses are the same as are the two outer terms. So the Lagrangian density is substituting this into the Euler-Lagrange equation of motion for a field. So the Euler-Lagrange equation becomes, the quantity in parentheses above is just the field tensor. So this finally simplifies to that equation is another way of writing the two inhomogeneous Maxwell's equations using the substitutions, where I, J, K take the values 1, 2, and 3. Quantum electrodynamics and field theory. The Lagrangian of quantum electrodynamics extends beyond the classical Lagrangian established in relativity, to incorporate the creation and annihilation of photons. In quantum field theory it is used as the template for the gauge field strength tensor. By being employed in addition to the local interaction Lagrangian, it reprises its usual role in QED.